Thank you very much for the introduction and for the invitation. It's a pleasure to be here today. I really appreciate this conference. It's the first time I attend. I will talk about B-Spline image-based models, and also about the way we use image-based model to help digital image correlation. So we are interested in cellular materials because of their high specific performances, and we are both interested in random architectures like on the left foams, but also on periodic or quasi-periodic patterns which are used in so-called lattice materials on the right. There are many applications, among which lightweight structures, energy absorption. So they're used in medical implants, and they're also interesting because they have multi-physics properties like thermal management or electrics. When we want to characterize the mechanical properties of such material, we usually perform in situ testing, like it was discussed yesterday, in situ and X-ray computed tomography. So we put our sample in a specific compression machine inside the tomograph, and then we have different images of the sample at different loading stage, and then in order to better quantify the analysis, we perform what we call digital image correlation, which is an image matching, image registration techniques. As Fabrice already explained that yesterday, I won't go further into detail, but digital image correlation or image registration, the idea is to solve this equation, the gray level conservation equation, where F and J are the data, the images, before and after loading, and the unknown is U. This is a scalar equation. We have just one equation and at least three unknowns, because we have three possibly components of the displacement in 3D. So this is a severely ill-posed problem that requires regularization. Everything was said yesterday. There are two ways to regularize such a problem. There is what I call strong regularization. This is what Fabrice explained yesterday, which consists in reducing the size of the approximation space. And for instance, we play with the zone of interest, whose domain omega, its size, which can be interpreted as a length, in which the displacement is supposed to follow a low-order polynomial evolution. And then the more you increase the size of the subset or other element, the more you regularize the problem. Another approach, which was also mentioned yesterday, is what I call the weak regularization. So you let your unknown behave in a large approximation subspace, but you penalize the short varying component of the solution by adding this red term here, which is a metric of the unknown. It can be, for instance, as said yesterday, the gradient of the solution. And in our situation, we usually define a metric that is related to elasticity. Lambda is a parameter which can be seen as a filter cutoff. So you can link this lambda to a certain length also. So there are two families of regularization. This is the kind of images that we have when we play with digital volume correlation with foams, for instance. The problem is that we have very small strats, very few numbers of pixels, and inside there is no pattern, which is necessary to make a digital image correlation converge at this scale. So what people usually do was explained also yesterday. People usually consider large size subsets, and they use the microstructure or maybe the architecture as a pattern. which was called yesterday by Fabrice the curse of DVC. I took some references of the literature. It's funny because Fabrice showed exactly the same kind of result yesterday, but I made my my slides two weeks late before, so it was not. So this is a compression test taken from the literature, a compression test on the bovine bone, and as you can see, digital image is very rich. You have a very fine description of the geometry, but when you use the architecture as a pattern, you must use very large subsets, and then you have a coarse or homogenized description of the displacement, the kinematics. So when you compute the strain, you end up with something which is smooth or homogenized. And we are frustrated because we wanted to have something more complex and better describe the kinematics of the bone walls. Another example of a pomelo peel under compression, you have a very complex description of the vascular bundles, but when you compute the strain, you obtain something very, very homogeneous. So in this talk, I will try to show you how we try to avoid this DVC curse by using an image-based model, mechanical model, to help DVC better describe the kinematics of such compression tests. There are several families of image-based models, as you know, in this conference, certainly better than me. There are voxel-based methods based on gray levels, voxel-based methods based also on thresholding, FFT-based. There are also conforming methods like marching cues, marching squares, that aims at building a FE mesh that fits the boundary of the domain. There is also a family called unfitted boundary method, like it's also called a fictitious domain method or finite cell method or cut-fem. There is plenty of words also to describe that. It consists in putting a structured regular mesh that does not conform to the shape of the analysis domain, and then you build a quadrature rule inside the domain only. I will come back to this later. And another way of building models, that what I will talk about after, is in computational mechanics. We also have simplified theories like BIM models. BIM models, it consists only of a line, and the cross-section are interpreted as line mechanical properties. And I will show how to build this kind of model that are very cheap because there are a very small number of degrees of freedom. Sorry. And what I have in mind each time is that I try to build what I call fairly priced models. It means that I know that the pixelization and the quantization of the image make me lost some information, and I want to build the better solution I can, but avoiding overcomputation, because I know that my geometry is not correct. So there are three parts. The first part will be very quick. It's about the families of method called fictitious domain method. Then the second part, I will explain how I build BIM-based model, so wires from images. And then in the last part, I will try to show you how mechanical image-based model can improve digital image or digital volume correlation. So I also like to analyze the error, the different sources of error. So I used to play with ground truth data sets. So I start with a true analytical description of a fictive model, and then I assume that I also have the associated closed form solution. So it's a mechanical field like displacement or strains, and I always try to compare to that. And then if I have the real geometry, I can generate synthetic image with gray levels and pixels. And then from this image, I can try my algorithms to build a geometric model of from this image. And if I compare the geometry I obtained from the image-based geometric model to the real geometry, there is what I call an intrinsic geometric error that will pollute everything in the following of the analysis. And I try to the other sources of uncertainties or errors, like finite element shapes, the size, the integration, etc., will be added to this one, so it's not necessary to overcompute the simulation afterwards. Just a small slide on fictitious domain methods, so you can see that there are plenty of other names. The idea is to put a regular grid on the domain, on top of the domain, and then you don't have to mesh to conform to the geometry. It's only the quadrature rule that has to conform to the mesh. So you divide each cells into subcells in order to well describe the geometry from an integration rule point of view. So there is a lot of parameters in numerical parameters like the size, the degrees of the shape function. We are using usually high order finite elements or splines. So there, the degree, the size of the elements, and also the number of subcells that add errors to the simulation. And if you, in the end, you have the true geometry, you have the reconstructed geometry, so you have the intrinsic geometric error, and then because of your parameters of the simulation, like size of the finite element, number of subcells, you add also new errors. You end up with a sum of different sources of error, and if you don't pay attention to this, you may use too fine simulation. And in practice, if from a computational point of view, we usually consider the geometry as perfect, and then we perform nice convergence analysis. For instance, this is the error versus the size of the elements. But if you consider both sources of errors, you can see that you reach quite quickly an asymptotic value, which is linked to the geometry that is not correct. And what we find out, which is quite logic in the end, is that your discretization must not be smaller than the pixel size. And then, when you have your model, you can also compute the simulated field with your mechanical image-based model. So you can compute a strain field, for instance, and compare to the closed form solution you had. And what I wanted to show you is that using a spline-based fictitious domain method, it's possible, this is the error versus the number of degrees of freedom, it's possible to obtain the same kind of error with approximately 1 order of magnitude less number of degrees of freedom as compared to classic first-order finite element approach. Yes, this is, for instance, the reference solution, the different gray level-based, voxel-based method, the conforming FEM with marching squares, and the proposed spline-based fictitious domain method. And we have only 800 versus 3 to 16,000 degrees of freedom. So this was the first part. The second part will be about how to go a step further. My goal is really to devise very cheap, with a very small numerical complexity models from images. And in mechanical engineering, we have what we call the beams. So it consists only of 1D lines or 1D curves that have mechanical properties. But from a numerical point of view, it's very cheap because you have only a small numbers of degrees of freedom. And my question was, how can we build from image such a model? And we based our work on the work of of Marc François from University of Nantes. He developed some years ago an algorithm that was capable to locate a line within an image. And I will try to explain you with a sample image which was taken with my phone of the charger cable of my phone. So the idea is we start with a spline approximation because we are doing geometry. So splines have very nice properties like high degree of regularity, but B-splines are polynomials with local support. So it looks like finite elements. You have shape function. For instance, you have here 4 shape functions in the xi direction. And you can build a geometry, the red line here. For instance, if you take a point in the xi direction there, to know its position in the physical space, you just have to evaluate all the shape functions at this very point xi and multiply each shape function by the position of the control point. It's a bit like infinite element with the nodes and the shape functions. The simple difference is that the shape functions are not exactly the same, and that the nodes do not necessarily belong to the geometry, whereas in finite elements it is the case. So what's nice with spline is that if you move one control point, you can change the geometry in a very regular way. There are plenty of other good points with splines. And now, if I come back to my problem, I want to build a geometry of a spline that fits a line in an image. I need to build a set of integration points or interrogation points. So I introduce a new dimension, which is eta in the parametric space, and I can map the point in the parametric space to the physical space using the spline mapping in the xi direction, and we use an identity mapping in the eta direction. It means that if you have a point 10 pixels above in the eta direction, you just map the point to the center line and go 10 pixels in the direction of the normal to the spline. So I can have a set of points, and I can map them from the parametric space to the physical space. And then if I put these points in an image, I can evaluate, thanks to gray level, subpixel gray level interpolation, I can evaluate the gray level of each point and bring it back in the reference parametric space. And my goal, if I do my job well, I need to move the control points in order to have in the parametric space something which is a line, perfectly horizontal line, which is not actually the case here. What I expect in the parametric space is something which is independent from xi, only dependent on eta. So I build a second image. So I add the real image, and then I build a so-called virtual image, which is something theoretical. I guess I'm supposed to have this in the image. Usually we just take a cosine, but we just have to consider it can be shown that if you have an odd function, it will work. And then at the end, I have the virtual image, what I expect to have, the real image back in the parametric space. And what I want is to align those two images by moving the control points that describe the geometry of the center line. So I try to compute the difference, which is the argument of the functional here, which is the difference between the virtual and the real image. So my goal is to make this residual as white as possible by moving the position of the control points. So I don't go further into detail about the math, but here is an example. You can see the convergence of the algorithm. The control points are moving, and the center line becomes better and better at estimating the position of the wire in the picture, and you can also see the residual at the top, which is decreasing and getting close to zero. Okay, so that's nice. I'm now capable to locate a cable in an image, but it's far from the phone. So what I need to improve to approximate or to compute a image-based model of a foam or of a lattice is that I need to consider varying cross sections, because up to now it's only with a constant cross section. I need to estimate also the cross section, because it's a parameter of my mechanical model after, and I also need to handle connected and branching beams. And also one point which was not so easy for me, it was to start with something with the good topology. So what we did is just modifying the way the virtual image was defined. The virtual image was only a function of eta, and we decided to make it dependent also on xi, just by changing the period or the frequency of the cosine function. And the period of the cosine function is now defined as a spline interpolation. So we introduce new lambdas, which are the thickness control parameters, that parameters the way the thickness evolve in the beam. So we also use splines, and now in addition to the control point position that modify the center line, we also have new control parameters that parameters the way the thickness evolve in the beam. So another stupid application, I promise after I have real examples. This is a cockpit of a mountain bike. I initialized it with a straight line with a constant thickness, and the algorithm is now capable not only to estimate the center line, but also the evolution of the thickness throughout the beam. We did ground truth analysis also with a quarter cylinder with a evolving thickness, and we were able to see that if we use a standard virtual image correlation as with a constant thickness, we are very sensitive to the initial thickness we put in the model if the cross section is actually evolving. And with the method that estimate the thickness, we are no longer dependent on this, and we have a kind of subpixel accuracy in the position of the center line. We can also see that we pretty well estimate also the thickness evolution with something that is close to pixel or subpixel accuracy. Now, an example which is a bit more complex with multiple beams connected. In fact, what I do is that I perform one digit virtual image correlation for each strut of this sample, and they are connected through, like what we do in finite element assembly. We ensure that the continuity of the beam by prescribing that the control points at the vertices are the same, and also we ensure continuity of the thickness. And this is an animation of what we obtain. So in the end, our numerical model is only based on the black line. The gray line is only something which modifies the mechanical properties of the center line, which is black. So we now can do numerical simulation with only the control point, which are the black dots. And there is a very, very little numbers of degrees of freedom for the mechanical analysis. This is a more better analysis of the convergence of the algorithm. So you have here the geometry as compared to the image, and here you have the reference, the real image and the virtual image. And you can see that you can also well describe the way the gray level evolve and the thickness evolve within the beam, and you can see also that the residual is far is far smaller than with the initial guess. And what is nice with spline beam model is that it is very easy to perform numerical simulation, and even with nonlinear in the nonlinear regime. So you can see here it's an auxetic foam, so we are not surprised to see that when we are in compression, the transverse direction is reduced, whereas when we pull it, it increases in the transverse direction. And then we wanted to analyze the predictive character of this model by comparing to a 2D classic 2D model based on image using marching squares with a 2D solid plane stress assumption. And here is the result. It's in a nonlinear, geometrically nonlinear regime. You have in blue the B model with constant thickness, and in gray and in orange, the beam model with varying thickness and the 2D plane stress simulation. And we are very happy that we can model this complex simulation with something like 1 or 2 order of magnitude less numbers of degrees of freedom. And a last example, which is a bit more complex because we assume that we don't have the CAD of the model, so we need to build an initial guess that has the good topology. And we did that using image analysis techniques that was already mentioned yesterday. We used skeletonization of the image, and then watershed, which helped us to labelize each strut. And then we were able to build an initial explicit description of the foam, and then it was possible to run the algorithm, and the algorithm was capable to estimate the complex geometry, the random geometry of this sample. Again, we can see that the geometry is well estimated and the residual are small. Again, we compared the very light beam model on the right with a classic 2D plane stress analysis with fast marching, marching cubes or marching square in this situation model. Again, it's a nonlinear analysis under compression. The results for the first 5% of deformation are not so bad. If we increase a bit, it's less accurate. At least the simulation are a bit different. But what was nice is that we were happy that we were able to correctly estimate the local bendings of each beams as compared to the 2D finite element analysis. Right, just a teaser of what we are doing now, but it's a very preliminary result. We are working on the extension to 3D of such a method using a spline-based approach like this. There are really recent work, and maybe the PhD student will come next year to explain you what it does. The last part of the talk is about, okay, now I have an image-based model. How does it help me to improve the digital volume correlation method? So I come back to this sketch. And since I have a true analytic model, geometric, and I have also analytic displacement fields, I can virtually deform my model and then generate or synthesize deformed image. And then by comparing the reference and deformed image, I can perform digital image correlation and compare to the field I was supposed to have, which is the reference here. And so this is the kind of images that we develop, at least in 2D. This is the reference image. This is elastic tension analysis. This is an elastoplastic analysis tension, and this is a nonlinear geometric elastoplastic analysis of the model in compression. And we try to see if we are able to estimate this displacement without any speckle in the struts. So what we do is we build image-based model. For this slide, it's based on finite element fitting, so it's based on marching cubes and marching squares. So we build a finite element that conforms to the model, and we use this twice. We use it for the interpolation of the displacement in the image correlation problem. So we try to seek the displacement between image using this mesh, and we try to measure the displacement at each node of the mesh. But we also use this mesh to build a mechanical model that will be put in the red term of the regularization on the right. So we use the elastic model to regularize the DVC problem. So we use this mesh twice. And then we obtain a displacement field that can be compared to the actual reference solution. To analyze this kind of images with a classic subset-based approach, here is the kind of subset size that we need to use if we want to make the algorithm converge. And if you compare, the first row is the displacement. On the left, you have the reference. In the middle, you have the subset-based blind approach. And on the right, the proposed, what we called ADDICT, is architecture-driven DIC. It's a DIC method with mechanical regularization, with a mechanical model that is based on the images. So if you just look at the displacement, more or less, it seems okay. But when you look at the strains, you know that all the struts are bending, so you expect to have a compression to tension in the thickness of each bins. That you can see that it's the case on the reference field. You can see that with our method, it's possible to more or less have this also. Whereas with a subset-based method with large elements, actually we only have a kind of homogenized displacement. I won't go further into detail on this, but the lambda, we have techniques to estimate it, to estimate the good wavelengths for regularization. And what I just wanted to show is that if you use a too large regularization length, then you become more in a strong regularization, so you force your displacement to be actually elastic, whereas it's not the case. So this regularization length has to be interpreted as a length below which mechanical elasticity helps the algorithm, and over which only the gray level makes the displacement to be computed. I come back to volume image and this compression test on a polymeric foam. Here is the reference and deformed image, and as you can see, there is a crushing that occurs. There are lots of local bendings, very complex, and we try to estimate that using the architecture-driven digital volume correlation. The first step is to use a macroscopic approach, which could be done also with a subset-based approach. The idea is to take large elements and use the architecture itself as a pattern. And when you do that, you see in a macroscopic view that there is something occurring in this region, but you definitely cannot see how each individual strut behaves. And the other approach, which is what we call the micro or the architecture-driven DVC, the idea is to compute an image-based finite element mesh And then with this mesh, we will solve the DVC problem, but we also build a mechanical elastic model to help DVC. And again, if we plot the displacement obtained with the coarse approach and the proposed architecture-driven approach on the right, if you just look at the displacement, you may say that it's almost the same. But when you look more closely to the local kinematics, you can see that the global approach is not capable to explain the local complex bendings and bucklings, whereas the approach we proposed was able to. If you look deeper into detail, you can see, for instance, this beam or this strut here, which is bending a lot, and with a homogenized approach, you could imagine that the strut is only stretching or bending dominated, whereas it undergoes, I don't know if it's buckling or bending maybe. And if you look at the strain distribution, you can see that with the global approach, or homogenized approach, you definitely see that something occurred in this region, but you cannot say in which individual strut the strain concentrated, whereas we assume that we have a better description of the localization of strain with the method based on mechanical regularization. So, three parts. The first was to say that we have to be careful about the geometric error when we build numerical models based on images, and also that spline-based fictitious domain method may be sometimes a good alternative to finite element methods. The second part is that it's also possible to build ultralight predictive model using beams. And the last part is that, okay, I don't think I have broken the curse of DVC, but maybe we did a small step toward in this direction. So thank you very much.